Hello, everybody. Welcome to today's Sun River U class. The Newberry Volcano is awesome. Presented by Joey Bard from the USGS Cascades Volcano Observatory in Vancouver, Washington. The observatory's mission is to keep natural volcanic processes from becoming natural disasters. Joey Bard is a geographer and geographic information science specialist there. Since we live very near to the Newberry National Volcanic Monument, it seems like a very pertinent topic for us today. A couple housekeeping things before we get started. We are recording this session. As you've probably noticed, everybody is muted and their video is off. We ask that any questions that you have that you put into the chat, which will come directly to Sun River U, and at the end we'll read them to Joey and he can answer them. That's everything. Why don't I turn it over to you, Joey?
Hey, Katie, can you hear me?
Yes.
Yes.
Yes. All right, great. Well, thanks. Great. Thank you so much, everyone, for being here. Yeah, my name is Joseph Bard, and I am a geographer with the U.S. Geological Survey Cascades Volcano Observatory. So first off, I'd like to thank Katie Keller and the Sun River U staff for the invitation to join you all today, and to you all for deciding to tune in. And I want to say that I regret not being able to join you all in person, but the current COVID protocols mean limitations on work travel. So the title of my talk today is Newberry Volcano is Awesome. And I love Newberry, and I think it is one of the world's most fabulous places. And I think we're just so lucky to have it right here. So I'm very excited to take you on a little tour. So let's go ahead and jump right in. Try to jump in here. There we go. So let's start with a little mental imagery word association exercise. So hold in your mind the very first image that pops in your head when you hear the phrase volcano hazard. And what does that look like to you? Is it possible that it might look something like this, like lava erupting from the Kilauea's lower east rift zone in 2018? Or perhaps maybe something like this, a big pyroclastic flow coming down the mountain at Mount Pinatubo in the Philippines in 1991. Or perhaps maybe for Pacific Northwest locals, something a little more like this. You have ash blotting out the sky after the eruption of Mount St. Helens in 1980. Well, volcanic eruptions can be very complex, and the hazards can take many forms. And all of these things have actually happened in the past at Newberry. If you're in the Central Oregon area, it is really hard not to notice the abundant lava flows that really surround the volcano. And while pyroclastic flows, which are these torrents of hot ash and pumice and gas, are rare at Newberry, they have occurred before. The most recent was around 1,300 years ago. And ash from past explosive eruptions has been blown very far downwind into neighboring states. Newberry has erupted in many different ways over the course of its history, and because of this, it remains an active area of scientific research, and visitors to the area are treated to so many interesting and wonderful landforms. So today's plan here is to introduce my organization and myself, and then we'll talk a little bit about the volcano's eruptive history and how these eruptions have shaped the local landscape. My approach for this talk is to start broad at a regional scale, and then move towards and eventually into the summit caldera of the volcano. And because of this place-based approach, we won't really stick to any strict chronological order of eruption history, but rather we'll talk about things we can see at different places. And eventually we'll wrap up the discussion with a discussion, talk about what could occur during future eruptions and how nearby communities can safely coexist with this amazing volcano. And then if you're still into it, we can do some Q&A. So my goals are that you will learn something about my organization and what we're doing to keep track of volcanic activity, that you will better understand what could happen if the volcano enters a new phase of activity in our lifetimes. You'll know where to find more information about Newberry and other volcanoes to help you safely coexist with this and other volcanoes that are surrounding us here in the Pacific Northwest. But I really hope that you'll take away some new information about the volcano that will help you to enjoy it in maybe some new ways than you have in the past. Okay, so first, just a little bit of background about the volcano hazards landscape in the US. So in the US and its territories, which include the Commonwealth of the Northern Mariana Islands in the far Western Pacific and American Samoa in the South Pacific, there are 161 active volcanoes. 55 of these are categorized as high or very high threat. And this is based on factors including the eruption history, these are frequency of past eruptions and the styles of past eruptions, and the potential for any of these eruptions to impact people and important societal systems. So I mentioned this idea of active volcanoes, but what is an active volcano exactly? Well, we define it in two main ways. One is that if a volcano has erupted since the end of the last ice age, which is around 12 to 15,000 years ago, depending on where you are. We recognize this is an important cutoff because much of the geologic evidence of past eruptions, or it's possible that geologic evidence from past eruptions could have been eroded away by meltwater from the receding continental and mountain glaciers at the end of the last ice age. But in addition to that, and perhaps even more importantly, we consider a volcano to be active if we can detect signs of an active magmatic system on a volcano by instruments that we place on the volcano. Now, all active volcanoes have some normal background activity. There's stuff moving around down beneath the volcano, magma moving around, gases, etc. But most of the times this activity isn't related to any sort of impending eruption whatsoever. So because of the threat that is posed by active volcanoes in the US, the US Geological Survey operates the Volcano Hazards program with the mission to enhance public safety and minimize social and economic disruption from eruptions through effective delivery of forecasts and warnings and information on volcano hazards based on our best scientific understanding of volcanic processes. Now, to carry out that mission, there are 5 volcano observatories that are distributed across our nation's volcanic regions. There's the Hawaiian Volcano Observatory, there's one up in Alaska, there's one in the Bay Area in California, there's the Yellowstone Observatory, and then there's the Cascades Volcano Observatory in Vancouver, Washington, where my office is, although I am coming to you today from Portland, Oregon. And the acronym for the Cascades Volcano Observatory is the CVO, and so I'll be referring I'll be using the acronym going forward here. And so you might have noticed on this map that Alaska has is the state with the most active volcanoes that are in this high threat category. And that is true, but the Cascades range has the most very high threat volcanoes that are clustered in one region. In Washington, there are 4 volcanoes. We have Mount Baker, Glacier Peak, Mount Rainier, and then of course, Mount St. Helens. In Oregon, there's Mount Hood, the Three Sisters, Crater Lake, and of course, Newberry. And those are indicated by the black arrows on this graph here. And then there's 2 that are in California. There's Mount Shasta and Lassen. So at the CVO where I work, it was formally established in 1982, exactly 2 years after the eruption of Mount St. Helens in 1980. And it was recognized that with all the active volcanoes that we have in the Cascades, it was a very good idea to have a permanent volcano observatory in the Pacific Northwest. So at the CVO, our area of responsibility of volcanoes in Washington and Oregon and Idaho. In addition to this domestic program, which we have at the CVO, we're also home to a program called VDAP, or the Volcano Disaster Assistance Program. And that is a partnership between the US Geological Survey and US Agency for International Development. And so what VDAP does is they donate expertise and equipment to developing nations with volcano hazards. And so this mission is humanitarian, but it's also diplomatic. But at the same time, by assisting with volcanic eruptions around the world, we can test cutting edge equipment in real life situations, and then we can prove the concepts and bring that equipment back home to help us to be safe from future eruptions here in the States. So at the CVO, we have 4 strategic elements that guide our work. We have volcano monitoring, we have hazards assessment, we have research, and then we have hazard communication with the public and authorities. So volcanoes are complex, and it takes many scientific and technical disciplines to understand how they work. So let's dive in just a little bit deeper here and take a look at what it takes to make a volcano observatory work. And in case you were wondering where I am in this picture, I'm right here in the back. All right. So who works at a volcano observatory? Well, we have around 90 people working in a bunch of diverse specialties at the CVO. And people who study physical volcanology and process modeling, for example, modeling magmatic processes or debris flows, and this is using computer simulation models. People who study seismology, this is detecting and interpreting earthquakes related to volcanic activity, and this is versus, for instance, earthquakes that are tectonic in origin. We have people who study volcano deformation. This is detecting patterns of regional and localized uplift that are in subsidence. They're related to magmatic intrusions beneath the volcano, and using equipment like high precision GPS sensors. With folks who study ash and gas emissions, these are geochemists, and they're studying the variations in gas types as well as the gas discharge. We have folks who work on our instrumentation and field engineering, and this is the crew who creates our network of sensors and our communication network to transmit the data that we collect on volcanoes back to the observatory for analysis. We have folks who do geographic information science like me and geographic information systems, and that's making maps, making products for communicating our knowledge, doing remote sensing and terrain mapping. We have a sediment laboratory, and that group analyzes the sediment that's in river systems that are attached to volcanoes. We have folks who do geologic field work, and this is maybe what you think of when people think of the US Geological Survey. These are folks who go out in the field and dig holes at volcanoes and help piece together the eruptive history of these volcanoes, which is really key for understanding how frequently volcanoes erupt and what type of eruptions a volcano has produced in the past. Additionally, we have folks who study earthquake, or have people who like earthquake studies, and this is actually like the experimental aspects of seismology. This would be lab experiments where folks are interested in how seismic waves propagate through rocks and rock physics and that sort of thing. We have folks who do outreach. This is interfacing with the public, forming partnerships with emergency management agencies. And of course, we have a fantastic IT and admin staff to keep us all running. And moving forward, we're really excited about hoping to grow our capacity in social sciences to make sure that some of the products that we're developing are really well matched to the needs of our users. All right, so who am I exactly? Well, I'm a geographer, like I said, and I do GIS analysis and support for our office. That's cartography, map making, I make graphics and that kind of thing. I work on our geologic map database products, outreach products. I make graphics for both internal and external public presentations and that kind of thing. I have an art background, but my formal training is in geography. And I started at the Cascades Volcano Observatory as a student intern back in 2012. So enough about me, let's talk about this volcano. All right, so let's just take a moment to look at the broader kind of geologic and geographic setting of Newberry. So Newberry is right here, nearly smack dab in the middle of the state. And so I want to overlay a graphic from an old publication that shows us some of the sort of the physiographic provinces of this. And so Newberry lies at the boundary between the Cascades Range, which is right here, and the Basin and Range province, which is right here. Newberry is similar in age to many volcanoes in the Cascades, and lavas from Newberry Volcano and the Cascades volcanoes actually are chemically similar. An interesting aspect of some of Newberry's past eruptions is they do share some characteristics with a sequence of rhyolite eruptions that get younger in age as you get closer to the volcano. And these are these lines on the map, and the eruptions actually get younger and younger as you get closer to the volcano. And so I brought up a term called rhyolite, and rhyolite describes a category of magma that is based on its composition, and I'll talk a little more about that later. So these ages range from around 10 million years old in the far southeast to to much younger, right around the volcano. And this had actually led some people to speculate that Newberry, where Newberry is related to the movement of a hotspot. But evidence from more recent geologic and geophysical and mineralogical research indicates that although Newberry might not look like other volcanoes in the Cascades, we don't get the charismatic stratocone, it is fundamentally formed by the same subduction-related processes as other Cascades volcanoes. All right, so as a reminder, here's Newberry right here again in the middle. So this illustration on the right of this map shows an idealized view of a convergent plate boundary, where the plate consisting of oceanic crust is being subducted beneath the more buoyant plate made out of continental crust. So locally here in Oregon, these plates are the North American plate, which is where probably most of us are sitting on right now, and the Juan de Fuca plate, which is off the coast. And they converge to form the Cascadia subduction zone and the Cascadia megathrust fault. So when the subducting plate reaches a certain depth beneath an overriding plate, the conditions are right to trigger melting of the rock into magma. And because magma is more buoyant than the surrounding solid rock around it, it rises up through planes of weakness in the rock and eventually will collect in magma chambers beneath volcanoes. And eventually, some of this magma will end up being pushed through vents and fissures and through the Earth's surface. And then once it erupts, we call it magma lava. So some volcanic eruptions are explosive and others are not. At Newberry, both types of eruptions have happened. And whether an eruption is explosive, meaning we might see plumes of ash high into the sky, or if it is effusive, meaning that the volcano is extruding lava or some combination of these behaviors, it mostly depends on the dissolved gases within the magma. And so two key factors that influence how much dissolved gas is in the magma are the magma composition, which controls how easily gas can escape from the magma, and then the rate of ascent of magma as it moves slowly and as it moves from down deep up into magma storage chambers and eventually can get erupted. So magma moves slowly to the surface, has more time to release gas prior to being erupted. And when magmas are gas depleted, eruptions are typically less explosive. Some magma is very viscous though, and for example, rhyolite magmas are very viscous and gas cannot escape easily. And as magma nears the surface, the gas comes out of solution to form bubbles that expand to many times their initial volume. And this is what forces magma to erupt explosively. And the classic example is just opening a soda bottle and the carbon dioxide bubbles, just appear in the liquid and the soda froths everywhere, right? And so just to kind of illustrate what this looks like in terms of the geology, if we had 1 cubic meter of rhyolite magma that was 900 degrees centigrade, and it contained 5% of water, dissolved water by weight. And then we were to suddenly bring it from depth to the surface, we would get an expansion. It would expand to 670 cubic meters as a mixture of water vapor and magma at atmospheric pressure. And so it's really this rapid expansion to hundreds of times the initial volume that is driving explosive eruptions. Okay, so Newberry Facts. So we're looking at this image. The image that we're seeing right now is Newberry as seen from Pilot Butte in downtown Bend. And Newberry rises around 4,000 feet above the surrounding terrain. And you can see on the flanks of the volcano, there's many conical features, these are called cinder cones. The volcano extends 75 miles north to south and 27 miles east to west for a total area of around 1,200 square miles, or about the area of the state of Rhode Island. It is the largest volcano in the Cascades by area. And the growth of the Newberry began around 400,000 years ago. And it's unlike a typical Cascades stratocone volcano, such as Mount Hood, that has that really kind of classic conical form. Instead, Newberry is called a shield volcano. And so it's named for its shape. It's more shaped kind of more like a shield. This is formed by lots of diverse lava types that have erupted over time. And at Newberry, there's over 400 volcanic vents. So these are the places where a vent is the term for the place where magma actually erupts from the ground. And a lot of these vents are aligned in this sort of in this orientation right here that reflects a strong regional tectonic influence. So at the summit, there's been very explosive eruptions that have occurred. A very large explosive eruption or series of eruptions produced the caldera at the summit. And ash from this eruption can actually be found as far away as San Francisco and the California Bay Area. So between the end of the last ice age and around 12,000 years ago and 7,700 years ago, Newberry Volcano has erupted at least a dozen times, and it is absolutely certain that it will erupt again in the future. However, there are currently no signs of any elevated activity. There are no signs that an eruption will occur soon, and the volcano is definitely not overdue for an eruption. And if there are signs that volcanic unrest is detected, the USGS will issue advisory and collaborate with authorities to help mitigate hazards. And I will talk more about this down the road. Okay, so from this regional scale, one of the stories I really love is how the eruptions over time have caused the Deschutes River, the Tumalo Creek, and the Crooked River to change their courses. This has been happening for a very long time and has helped to create some of the most beloved features in the modern landscape. So this map shows the estimated locations of the paleo channels of the Deschutes, Tumalo Creek, and Crooked River. Now, one of the things I want you to note is how right here, this is the estimated confluence of the Deschutes and the Crooked River from way back. And it was likely south of Smith Rock, but now the rivers join up here in Lake Billy Chinook. So around 350,000 years ago, these lavas that we call the basalt of Crooked River Gorge was erupted from vents on the north flank of Newberry that have now been buried by much younger lavas. Now, lava entered the Paleo Deschutes River channel and it flowed northward to the vicinity of Smith Rock, where today the lavas actually form the parking lot area for the park. This forced the Deschutes and the Tumalo Creek over westward, and the Deschutes established a new channel through the present site of the city of Redmond. The Crooked River was pushed to the north by this portion of the lava flow and established essentially what is the modern channel of the river today. So in this image of Peterskeen Ogden Wayside, we can see that where these lavas actually are nearly filled the old Deschutes River channel. And beneath this bridge, they have now the river has cut through around 180 feet of these lavas. About 75,000 years ago, a series of lavas were erupted called the Basalt of Bend. And these are erupted from vents that are buried near what is now lava cast forest. And these lavas flowed west to the modern location of Lava Butte, and it temporarily blocked the river, roughly around the upstream of where the Benham Falls is today. And so this diversion of the river actually created the dry canyon in Redmond, which is right up here. And prior to this, the Deschutes had been flowing through this channel down to the downtown Redmond for about 275,000 years. And so one of these places where you can actually get right up close to the Basalt of Bend is at a place called Lava River Cave, which is a lava tube that's over a mile long that is in the Basalt of Bend, and it's not far from Lava Butte as well. Okay, so around 70,000 years ago, lavas known as the Basalt of Lava Top Butte flowed into the dry canyon and partially filling it and forming the present-day flat floor of the canyon. After it emerged from the dry canyon over in this area, the lava again pushed the Deschutes to the west. So at this point, around 70,000 years ago, from a little bit south of Bend, the Deschutes has been flowing in its modern channel for up to where Lake Billy Chinook for around 70,000 years. Around 7,000 years ago, one of the most famous eruptions in the area occurred. This is the one that formed Lava Butte, where Lava Land's Visitor Center is located today. And this was the last eruption to change the course of Deschutes and create the modern channel of the Deschutes that we all know today. So in this map, you can see where the lava blocked the river, forcing it sharply north and creating Benham Falls. So while we were here at Lava Butte, let's stop for a few minutes and give it a closer look. And I know although most people who live in Central Oregon might actually already be pretty familiar with Lava Butte and have taken the trail there, I do want to spend a few minutes here talking about it for a few reasons. And one of them is that the trail is mostly wheelchair accessible, or at least a good portion of it is. And so it's a really great spot for lots of different people to be able to get really up close to a lava flow. And that's pretty unique, I think. And so, and also I want to show you a modern eruption that I think can help us gain some new appreciation for what we do see when we do visit Lava Butte. So two of the most prominent features of Lava Butte are this conical cinder cone and the lava flow that surrounds it that broke out from the bottom of the south side of the cone after the cone was fully formed. Now, Lava Butte was formed by what's known as a monogenic eruption. And we can break down this term in mono meaning one and genetic referring to heredity or history. And so the term monogenic means that an eruption occurs in one location just once. And this is in contrast with other volcanoes like the stratocone volcanoes, where they often have multiple eruptions from essentially the same source area. And so monogenic eruptions are common at volcanic rift zones. And that's exactly what happened here during this sequence of eruptions along Newberry's northwest rift zone. So rift zones are areas where there's extensional spreading of the crustal surface, and it spreads perpendicular to the axis of the rift. And so the rift zone at Newberry extends from the caldera down to Lava Butte. And within this zone, there's around 100, or at least 100 volcanic vents. And some of these lava flows that have been produced are over 20 miles long. So at rift zone, eruptive vents are commonly oriented in sort of parallel to the axis of the rift. So this series of eruptions produced some really fantastic features that we can see today, including the lava cast forest, which was created when lava flowed into a living forest and the lava was quenched on the trunks of the trees, and then the trees were lost to time and leaving behind these cylindrical forms in the lava. So on the map, while the cinder cones, you can see the conical features are very prominent. Many of these eruptions actually began as fissure eruptions along sort of linear cracks. And it's common that as eruptions, these type of eruptions progress, the magma will establish a dominant pathway to the surface, and the eruption will remain in one location long enough to build up a cinder cone around the vent. And if we want to know what these rift zone eruptions look like or may have looked like, we actually do not have to look too far in the distant past. In 2018, Kilauea Volcano on the island of Hawaii erupted in this volcano's lower east rift zone. And while the geologic setting of these two volcanoes is very different, the eruption style in 2018 probably looked much like what some of the eruptions in Newberry's rift zone. And so this next photo I want to show you is a thermal image. And in the light gray areas, light gray and white areas, these areas are hot in comparison to the surrounding terrain. And this is where you can see lava just erupting from these really linear features that are all aligned with the axis of the rift in Hawaii and on Kilauea. And so I want to show you a video of what part of this eruption looked like. There's a couple things I want you to notice, and that one is that this video is awesome. And the next thing is that you can see these globules that are falling off of they're coming out as they're being found, they're coming off of the fountain, the lava fountain, and they're falling down to the ground surrounding the volcano. And this is, or around the vent, and this is what's building up, and they're building a cinder cone essentially around around these fountains. And then in the foreground, you can actually see some lava there's a lava cast forest potentially being created right there in real time. As you can see, the lava sort of engulfing some of those trees, and maybe once those trees are lost to time, there'll be those lava casts there as well. All right, so a few more photos here of the Kilauea eruption. On the left photo, you can really see here how these eruptions are occurring along this one linear feature, which is the axis of the rift. And so the upper photo here shows about 150-foot tall fountain of lava at a place that became known as fissure number 8, and this was the place where the eruption really focused. And the lower right shows this horseshoe-shaped feature that this is the cone that was around fissure 8 when this is fissure number 8 at the end of the eruption and when it stopped erupting. And this is from the lava from the fountain falling to the ground and sort of just building up this cone. So if we return back to Newberry, we can see some features here at Newberry that look really similar to some of the stuff we saw in the video of the Kilauea eruption. So on this left map, in this circle shows a vent that looks kind of like a pit with a little mound around it. And I think this feature might have been built by eruptions that look really, really similar to something we saw in that video. You can see there's some other pits here, and they all kind of align with with lava butte on illustrating this axis of the rift. And this other map we have the red arrows, and that's showing where the lava breached through the base of the cone after it was fully formed and flowed out all around the cinder cone. So on the right map, on the bottom here, we can see this feature down here, and I think it looks real similar to this one here at fissure 8. And this one is called Moxed Butte, and it is just a little bit north of the lava cast forest area. So I think that's pretty cool to see that. All right, let's take a trip up the hill into the caldera and back in time a little bit and talk about the sequence of eruptions that created the caldera. So zooming out to our regional scale here, and then we're going to go from here up to the top of the mountain, and we're going to zoom into this box right here. Okay, so I mentioned the word caldera, so let me offer you a definition of what caldera is. A caldera is a large basin-shaped volcanic depression that, with a diameter that's many times larger than any individual volcanic vent. In fact, calderas can contain volcanic events or volcanic vents, and Newberry caldera definitely does. And so calderas can range from up to a mile to up to 30 miles across. And they're commonly formed when magma is either withdrawn or erupted from a shallow underground magma reservoir. And when you remove a large volume of magma from beneath the volcano, there's a loss of structural support, and the overlying rock will collapse down to form this big depression shape. Calderas are different than craters, which sometimes they're colloquial. The terms are interchangeably used colloquially. And craters are actually smaller circular depressions, which are created primarily by explosive excavation of rocks during eruptions. So I want to show you a little diagram of this caldera from a geologic map of Newberry to help illustrate the concept a little bit further. So if we rotate our map to right here, and then we imagine we were going to slice the volcano in half right here, and then look at it at its side from this angle, we might see something that looks a little bit like this in cross-section of the caldera. So again, if you remember, let's talk about the processes of this caldera formation again, and that occurred around 75,000 years ago during a major explosive eruption episode and this collapse event. So if we remember, magma ascends from the storage chamber, and it looks like, and it's going to be erupted here, and it looks like it probably was maybe from this diagram that might have gone right out of the middle of the volcano, and that is a site of an eruption, but that is an eruption that came much later than the formation of the caldera. So then once this magma is erupted from the caldera, and once you get a large volume of magma is erupted, and without the support without the magma beneath the volcano to support the top, it collapses on these things where the yellow dotted lines are called ring faults, and then sinks down. And so there's evidence to suggest that there are maybe even 3 caldera forming eruptions that created big ash plumes and pyroclastic flows at the volcano. And so the reason is because this collapse structure actually has several nested walls, one inside the other, and this indicates more than one set of ring fractures. Let's take a look at our map here again. And I want to overlay a section of that geologic map that cross section came from over this topography to show you the locations of these ring faults. And so here the ring faults are shown with these dotted black lines, and I'll highlight them with a couple of arrows here just real briefly. So the multiple ring fractures that might have formed, it's possible they might have formed during a single event as multiple blocks collapsed or slumped in sort of, in some sort of sequence along the margins of the caldera. But probably the more likely interpretation is that it's a collapse. The collapse is associated with a sequence of eruptions that occurred relatively closely spaced in time. And so today, these faults are totally concealed by younger material that is overlying them. And so their locations are entirely inferred from the surrounding topography. But if we bring up this cross section again, we can see that, between these brackets, these are layers of younger material that have since filled in the caldera since the collapse. So if we zoom out just a tiny bit here, on the west side of the volcano, there are a couple of regions where you can still find ash from this caldera sequence, or this sequence of caldera eruptions. But the very, very best place to see these deposits from these eruptions is at a place called Palatal Creek Falls Overlook, where the creek drops over about 100-foot cliff that is made up of a rock type called welded tuff. And the term welded tuff describes a rock that was formed when ash fell to the ground, but it was still hot enough to refuse together and then cool into a layer of solidified rock. So most of our knowledge of what's beneath the modern caldera surface comes from a geothermal exploration drill core sample that was from this hole was drilled pretty close to the center of the caldera. And there's some really interesting things they found when they looked at the core. And one of them was that they found lake bottom sediments from around 950 to 1,050 feet. And this indicates that at one point the caldera was actually much deeper than it is today. To find hundreds of feet of lake bottom, essentially like mud that was at the bottom of the lake. It also shows that the central block of the caldera has subsided as much as even 2,500 feet from the surrounding caldera rim. So beneath the lake sediments, there's some ash flow deposits that go from around 1,050 to 1,640 feet below the surface. And these may be products of pyroclastic eruptions. These are eruptions that throw ash and pumice up into the air. It's possible that these could be associated with the caldera collapse, but they're chemically dissimilar to the ash flow deposits you can find outside of the flanks. So it might be from a different series of eruptions. It's unknown at this point. And so below this ash layers is layers of lavas. And so these lavas might be pre-caldera rocks of Newberry Volcano, but alternatively, they could be lava flows that filled in the caldera after it was created, in which case there would be beneath this, there would be another sequence of rocks related to the explosive eruptions at even greater depth. So I guess suffice to say that the story of the formation of the caldera is still being uncovered and will continue to be an area of active research moving forward. So let's turn our attention to the youngest and perhaps even the most spectacular feature of this volcano. And that is the Big Obsidian Flow, which is located right here on the map. And I find the Big Obsidian Flow to be completely stunning. And I think it's got a cool story too. The story of the eruption actually that caused the Big Obsidian Flow has three parts. So part one was a very large ash-producing explosive eruption. So I want to zoom out for this part just a little bit, and we'll come back into the caldera for the rest of the story. So this yellow triangle in the middle of the screen here is the location of the volcanic vent where the explosive eruption took place. And so this eruption began with a gas-rich explosive phase that produced a very high column of tephra above the vent. The resulting pumice fall deposit is called the pumice of Newberry, and that was carried by the wind east. The winds are blowing from the west to the east, and this deposit now mantles the east flank of the volcano. Around 5.5 miles from the source from the vent, the ash deposit this fall deposit of pumice is around 12 feet thick. And even 40 miles away from the volcano, it is still 10 inches thick. And so, we had strong westerly winds, and they carried these. The day that this volcano erupted, there was strong winds blowing nearly due east, and it blew ash all the way into Idaho. And so the lines of this map are called isopachs, and they're the concentric lines here that I've put up on the screen. And what isopach lines are is the lines that connect point measurements of equal thickness. So in this case, the measurements are the thickness of the pumice fall deposit. And in the real world, this ash fall deposit extends well off the screen to the right. So now I want to zoom back into the caldera for part two. I think I'm zooming. Try again. Yay. All right. So let's reorient ourselves. Again, here's the big obsidian flow. So part two of the eruption was less explosive and produced the Palatal Lake ash flow, which is right here. And this extends from the vent area over this broad area from the vent down to the current location of Palatal Lake. And the big obsidian flow for certain is now overlying some portion of this Palatal Lake ash flow. And then so finally, during the final stage of this eruption, the magma had lost much of its gas and flowed onto the surface to form the big obsidian flow. And obsidian is a natural glass that has no crystalline structure. So let's take a picture of some of the big obsidian flow, and then we'll talk about some cool recent research that might explain how obsidian lava flows are formed. So in the upper photo, we can see the lava flow as viewed from Palatal Peak, and you can see that the vent is on the right side. There's kind of a little dome-shaped feature there. So in the bottom left image, we can see a bunch of this banding and folding of the lava flows, and both of the darker and the lighter bands are made of the same rock, but the textures are different because of the conditions of eruption and the conditions of emplacement. And then in the bottom center and right images, we can see just some other different patterns of layering between the obsidian and the lava rock. So until recently, the mechanisms of obsidian formation had not actually been that well understood, and there were still many questions about how and why some parts of lava flows, like the big obsidian flow, were obsidian, while others were not, and despite being composed of essentially the same material that, from chemical analyses. And so there were definitely a few ideas about it, but in historic times, there had actually never been an eruption, or there had never been an eruption of an obsidian-producing lava flow, nor had there been the technology to mathematically model the dynamics of the eruption, using computer simulations, as it moved towards the surface from down deep within a volcano's magmatic plumbing system. So as I mentioned previously, eruptions are driven by the growth of bubbles that form when dissolved water and other gases come out of solution. Now, gas-rich magmas can cause violent explosive eruptions, while gas-depleted magmas can form lava flows. So lava flows can occur in conjunction with explosive eruptions or without. There's really a lot of factors that go into determine eruption dynamics. But if we recall the discussion earlier about how the composition of magma and the ascent rate are really key factors to the retention of gas. So obsidian is a product of a high silica mineral content magma called rhyolite. And this magma is highly viscous. And in contrast to lavas, this contrasts with lavas like what erupted at Lava Butte, which are low in silica mineral content and are thus much more fluid. And these lavas are called basalts. So in this image, we can see this rock has a very foamy texture and very clear evidence of gas bubbles. So back in the 1980s, it was suggested that it's possible that obsidian was formed as foamy rocks like this collapsed to form gas-poor, bubble-free glass as gas escaped through a network of interconnected bubbles. And this was known as the permeable foam model. However, there's one kind of key criticism of the permeable foam model, and that is that it's kind of inherently self-limiting, because as gas escapes, there's a certain threshold is reached where bubbles are actually no longer interconnected, and some proportion of the gas would then therefore remain trapped and be no way for it to escape and form this really bubble-free glass that we see in the field. But however, new research has suggested a new explanation that's different than the permeable foam model that might be really useful for helping us to understand the formation of obsidian lava flows and what might have happened during the sequence of eruptions that ended up creating the big obsidian flow. And so this is a graphic from a 2020 paper by Wadsworth and others that shows from left to right an eruption transitioning from an explosive phase where it's generating pumice and ash to an effusive phase where the main product is lava flows. And these are very hypothetical cross sections of this conduit, which is where the magma travels from down deep up to the surface, and the vent, which is the location at the surface where it is erupted. Now, if we remember, the big obsidian flow started as a large explosive eruption in which ash was transported as far away as Idaho. And then there was this phase that produced the Palatal Lake ash flow, and finally the big obsidian flow. So on this, so in the explosive phase, which is the leftmost image on this graphic, above this, oops, that's gonna happen at least once. Above this depth, the gas expansion is causing the formation of bubbles and this fragmentation of the magma into pumice and ash. However, beneath this depth, right here, the authors of this paper suggest that the magma is actually being ripped apart and gas is escaping without the bubbles forming first. The pressure is still too great at this depth. And as the explosive phase continues, this gas poor magma where the gas is escaped by this ripping apart process begins to stick onto the walls of the conduit in sinter, which means that it fuses together and on the walls of this conduit. And so finally, and then next here in image C, the eruption enters this hybrid phase. So it's still producing ash, but this effusive phase begins to emerge when the conduit starts to narrow, and lava flow begins to emerge, along with the occasional chunk of obsidian glass still being ejected. And when this happens, we call these things ballistic bombs, and being hurled from the volcano. And so finally, we get this transition into an effusive phase where the eruption is producing an obsidian-rich lava flow that is being this gas poor eruption, this gas poor lava is sufficiently aggregated to form these obsidian-rich lava flows, which are being stretched and folded as it advances down the slope. And so now that was a very generalized and simplified summary of that research paper, and it's much more likely that all these things, that it's not four discrete phases, that these things happen along a continuum, and it's definitely even possible that during the course of an eruption, you might go between these phases and back and forth too. So keep that in mind. So in 2011, in Chile, there was a volcano called Cordon Calle that erupted, and this was the first time in recorded history that a rhyolite obsidian lava flow had actually been directly observed. And as it turns out, the observations and the modeling that Wadsworth and others have done were really consistent. And so in the left image, we're seeing a lava flow, and there's also this plume of ash coming out of the vent. And so this might be this hybrid explosive or effusive phase. And finally, on the right is the area after the eruption had stopped. Another really interesting note about this eruption was the lava flow actually kept moving after the eruption had stopped for up to a year after the eruption completely ceased. And this is because the outer rubbly layer of the lava flow was very insulating, and it kept the core of the lava flow at a high enough temperature that it was able to remain mobile and continue to creep downhill. All right. So let's move on to this question. What might happen during the next eruption of Newberry? Well, the past is the key to the future, and by studying the deposits from past eruptions, we can really try to understand the behavior of volcanoes. And so in general, future eruptive events are often much more similar to more recent events than they are in events in the very distant past. And so what this graphic shows is all known eruptions in the Cascades volcanoes over the past 4,000 years. And we can see that Mount St. Helens, which is the fourth one down is far and away had the most eruptions in the recent past. And this is in contrast with Newberry right here, which has only had 2 eruptions in that same period of time. However, if we look a little bit further back, we can see that there's definitely been some more eruptions at Newberry in the past 15,000 years. And these have occurred both inside on the caldera and on the flanks. So to answer the question of what might happen during the next eruption, it really probably depends on where the eruption occurs. A flank eruption would most likely be basaltic if we're thinking lava butte, or other type of rip zone eruptions. And some of the youngest eruptions of this type happened along the northwest rip zone. So if the volcano were to become active and erupt on a flank, it would definitely not be surprised if it occurred somewhere along the north rip zone, but that is definitely not a given. Recall our example, Kilauea of a rip zone volcano. The caldera would likely be the site of the most of a rhyolitic eruption, or other types of dangerous explosive eruptions. Rhyolitic eruptions have been restricted to the caldera in the past 10,000 years. And these are some of the youngest actual eruptions that have happened at Newberry, have occurred in the caldera. Rhyolite magma tends to erupt more explosively than basaltic magma, owing to the increased amount of gas that's trapped within it. And geologists use this term pyroclastic, which literally means fire broken, to describe these explosive eruptions and the resulting deposits. Pyroclastic eruptions present the greatest threat to lives because of their violence and the great speed at which material is erupted from the vent. So if signs of increasing activity were detected in the caldera, the possibility of an explosive eruption would definitely be of concern. So recall our example from Cordon Collier in 2011 of a rhyolitic explosive eruption. So Palatal Lake actually, though, could present a couple of different hazards as well if an eruption were to occur. If eruption were to occur beneath the lake, the rapid mixing of water and hot lava could potentially generate explosive eruptions. Another possibility is if a really large volume of erupted material were to enter the lake very quickly, this could cause a large flood down the Palatal Creek drainage, which could reach the Lapine Valley in around 30 minutes or so. And so areas that are in that valley alongside the drainage would definitely be a priority for evacuation should an eruption look like it might be imminent in the caldera. So in addition to the possibility of this kind of flood, there's a similar event which is called a lahar, which is where these watery flows of volcanic rocks and mud surge downstream like rapidly flowing soupy concrete. And these might be caused by a rapid melting of snow and ice during an eruption. While these are possible at Newberry, the volcano is not very steep in comparison to a volcano, for example, like I'll use our classic example of Mount Hood. There's also no glaciers at Newberry. And so a lahar is unlikely to be as large or travel as far as it would on a steep-sided and glaciated volcano. So I want to show you the simplified hazard map of Newberry. And so this region is the lahar hazard zone. This is the zone that might be impacted if there was a flood from Palatal Lake. This zone right here is the near volcano hazard zone, where this is where we most likely anticipate really high energy hazards associated with explosive eruptions. And this basically outlines the caldera right here. So in this region is the shield volcano hazard zone, and this shows areas where we're probably more likely to see lava flows and less explosive eruptions. So one other thing to note is ash hazards are not shown, and this is in part because ashfall is really dependent on wind direction. And while the prevailing direction of wind is mostly from west to east here in the Cascades, any given day the wind can blow strongly in any direction. So it's also possible for the ash from another explosive eruption at a different volcano nearby to impact this area. For example, depending on the size of the eruption and the wind, ash from an eruption at Three Sisters, or actually in many other Cascades volcanoes, could easily fall in this region. And so one of the final things I want to say about future eruptions is that the volcano has not erupted in over 1,000 years. There are no signs of elevated activity. No eruption is imminent, and nor is the volcano overdue. But it's also fair to say that we cannot say when the next eruption will occur, nor how large it will be. But our best defense is to be prepared. So I want to segue to talking about safely coexisting with volcanoes. So this image is a map of volcano monitoring stations at Newberry in around Central Oregon. This is taken from the USGS Volcanoes website. So the USGS owns and maintains many monitoring stations, as well as we partner with agencies like the Pacific Northwest Seismic Network and other agencies as well to monitor these volcanoes real time and 24 hours a day, 7 days a week, to both keep track of the normal background activity of these volcanoes and to detect any changes that might occur that indicate that the volcano's level of activity is increasing. And these stations include very sensitive GPS equipments and seismometers, GPS instruments and seismometers. And these measurements are sent in near real time to the Volcano Observatory for analysis. And so if changes were to be detected, the USGS would alert state and local authorities as well as the public. So globally, volcanoes nearly always provide signs of elevated activity from hours to weeks before an eruption. It is extremely likely that the instruments on this and other Cascade volcanoes would detect these signs, and alerts would be issued, giving people ample time to take protective actions if a volcano was to, if elevated activity was to be discovered in any of these volcanoes. And so one way that the USGS would communicate about volcanic activity is these volcano updates. And so you were all invited to sign up for the VANS, the Volcano Notifications Service. And so this image actually is a screenshot I got today. And so there's 5 volcanoes currently that are in elevated status in the United States. 3 of them are in Alaska and 2 of them in Hawaii. One of them is Kilauea, which is currently erupting. Actually, 3 of them, there's a couple of them in Alaska erupting, but one of them is in this advisory. It has an elevated advisory, but it's not currently erupting. That is Mauna Loa. Social media is a really great way to stay in the loop with us. You can reach out to us at USGS Volcanoes on Facebook and Twitter and Instagram. We're really responsive to questions here. In addition, you can always email vhpweb@usgs.gov. We'll almost always get back to people within the week. It won't just, you're not shouting into a black hole if you want to get in touch with us at the Volcano Observatory. Also, please visit the USGS website. There's a number of really great pages with a ton of great resources about volcano hazards, both very specific volcano hazards and just hazards in general. In addition, if you have information, about monitoring, preparedness, and even specific things for where to get additional information in other states, for example, Oregon here. And one of the examples of the information you'll find on this is what to do during an eruption. So during a volcanic unrest, it's really important to follow the recommendations from officials. Local and state authorities are in charge of managing emergencies within their jurisdictions. So officials will update hazard zones and disseminate new maps and information as eruptions develop. If you're on a volcano during an eruption, which is highly unlikely this would ever happen unless you went there because the volcano was erupting, please move away from the volcano as fast as possible and really do pay attention to signs of closures of volcanoes. It can definitely save your life. And if a volcano is erupting and you are near it or downwind, there might be a couple of hazards to be aware of. One is lava flows, especially a place like Newberry. So if local authorities issue evacuation routes or evacuations, I would highly recommend following their advice. And you want to stay off fresh lava flows. Not only are they extremely hot, but the burning vegetation that is when lava flows over vegetation, this burning vegetation can release methane gas, which can accumulate in areas, and then it can be ignited and explode. I think actually the only person who was injured in the 2018 eruption of Kilauea was actually injured this way by a flying rock from a methane explosion, and this person did not evacuate. And so you might be in certain areas, you might be at risk from lahars if you are in a river valley where the river originates on a volcano. Some of these low-lying areas are potentially at risk for lahar hazards, and so really key to evacuate if you're called to in these areas. If there's volcanic ash fall, you want to seek shelter to minimize your exposure to ash. Unless it's absolutely necessary, you want to avoid driving. The ash can be really damaging to mechanical equipment, including your car. The ash on roads can create a situation of both poor visibility and make the roads, there's not much traction. You want to try to keep outside air from getting in your house. You want to, if you have non-essential openings, windows, and that kind of thing, you might even want to duct tape them closed, put damp towels at the bottom of external doors, and be careful about using your HVAC system to, you don't want to draw in fresh air from the, or maybe it's not quote unquote fresh air from outside. Maybe outside air is the better term to use. In addition, listen to reports. Follow us on social media, sign up for bands, keep in touch with the news, because if ashfall might be significant or it might just be just a nuisance. It really depends on the size of the eruption, the style, the duration, and so on. So yeah, please just follow. Following these recommendations are really the best way to stay safe during an eruption. So with that, unless there are any signs of increasing activity at volcanoes, we should all fully enjoy and appreciate volcanoes for the amazing places that they are. I fully stand behind my claim that Newberry Volcano is awesome, and there are just so many ways to enjoy this special place. So I'm going to stop there, and if there's time, I will do best to field any questions that you have. So thank you so much, and again, for being here today, everybody.
Thank you, Joey. That was great. We do have a question. What determines if a volcano is being overdue for an eruption? So
the idea about overdue is it's kind of a misconception. It's not really how volcanoes work. So that the idea, it could be. I think I have a little slide here that let me see if I can pull this one up. There's gonna be a great talk about this 1 week from today, actually, about Yellowstone, because this is something that comes up a lot with Yellowstone, is this idea that eruptions are overdue, and it's just not how volcanoes work. So we don't have to worry about that. I hope I answered that question, but yeah, that's just not a thing.
Okay. So far, that is the only question. If anybody else has one, type it into chat. We'll give a couple seconds for that to go by, see if anything else comes up. Here's one. Is there a connection between Newberry and Mount Bachelor?
Only in the way that they're both created by the same subduction zone processes that create the volcanoes all up and down the Cascades chain. So they don't share a magmatic system, so to speak. They both have their individual systems, but they're all kind of part of this. It's sort of at this really broad scale. They were both created by these subduction zone processes that are happening as the Juan de Fuca plate is being subducted beneath the North American plate.
Got another one. Your chart near the end showed 4 locations with red dots signifying activity in the nearby Cascades within the last 2 hours. What kind of activity is that? Oh, great. Yeah. Good eye. So these are this is a plot of earthquakes. And so this is one of our monitoring maps where you can kind of keep track of them. So these are all very small earthquakes that have been detected, and this is from a couple of days ago. This when I pulled this slide, but this is updated live all the time. And so yeah, these are just really small earthquakes that are detected around at different volcanoes and regionally around. And this is just totally normal background activity within the Cascades. So yeah, if you go to the USGS. So I have it here. Each one of these volcanoes has their own individual monitoring map, but you can zoom in and out to the whole Cascades or zoom around from each of these pages. So if you go to USGS, .gov volcanoes/Newberry, you'll find this map on the page, and you can zoom around and see what's happened earthquake-wise in the last up to the last 4 weeks. Okay, we're getting a lot more questions now. Okay, great. I didn't realize a volcano would span such a large area, 1,200 square miles like Newberry. Is that common? That's a good question. No, I would say no. I mean, most of them, it's definitely the largest by quite a bit. And I guess it's always tricky to figure out like where a volcano starts and stops exactly. But yeah, it's a pretty large volcano, and most of them are not nearly this large. I don't have an encyclopedic knowledge of all the volcanoes in the world, but yeah, this is a pretty big one, and so it's pretty special. Okay, how tall did Paulina Peak get before it collapsed? Oh man, I had this. I can't quite remember. I think it was something, about maybe 1,000 feet, 1,500 feet. I mean, it was speculated. Of course, it's all speculation. There's no real way to actually tell. But if you kind of like assume a certain, an angle that is common or with other volcanoes, you can maybe assume that it was around 1,000 to 1,500 feet, but there's no real way to know. would you mind telling us the website again to receive the daily updates on the volcano activity?
You bet. I will. Let me pull this page up again here. Yeah, so this would be volcano or usgs.gov/volcano/volcano-updates.
Great.
And if you just Google, USGS volcanoes, also you can just Google USGS volcanoes and it'll take you right to our page, and you can cruise around and you should be able to find these notification services, as well as, I should also mention that, you're welcome to email me, and this other email that's on this next slide here is a really great way. If you have any other further questions about notifications or any volcanic activity, let me click over here. Yeah, this vhpweb@usgs.gov is a direct line to answers about volcanoes. As is the social media. There's really active, a lot of great questions come in and get fielded on social media. So if you have any questions about this, and these social media is a really great place to stay in touch about volcanic activity too. There's always really great posts about how the eruption is changing. Since the Kilauea thing is going on right now, there's just been so many great posts about that, and just how it's nearly every day, it seems like there's just cool different changes and different ways that they're showing different interesting aspects and features of it, and it's different as new research and new observations are being discovered, they're putting them out on the web for people to check out.
Okay, next one. What's happening with the bulge being watched near the Three Sisters?
Ooh, that's a great question. Man, there's just a paper that just came out about that. I haven't read the paper yet, but yeah, as far as folks can tell, that there was that might just be part of this idea of that volcanoes sort of breathe, so to speak, where you have these patterns of regional and regional uplift and subsidence that happen. And if there hadn't been GPS instruments out there, we might have never even known it would have happened, because the movement is imperceptible when you're on the ground. And so we don't know that worldwide that would actually be really more common than we think, that kind of thing. But there is a new paper that just came out about that, summarizing the last 20 or 30 years of that research. I wish I had it close by. I could link it to you all.
How much warning time would the USGS be able to give us if an eruption was likely?
Yeah, that's a good question. It's one of those things that you hate to say it, but it definitely depends. I mean, there's no set time that from once a volcano starts showing signs of elevated activity to when an eruption might occur. And some of these volcanoes are such a small sample size that we don't really truly understand their behavior over time. And so we kind of look for global analogs to help us with that. And yeah, it's almost always, very infrequently is it hours, mostly. And if we think back to Mount St. Helens, definitely, I'm trying to remember exactly the dates from that. So it erupted on May 18th, but in late mid-April, I believe. So there was nearly a month of lead up time to that, and there were some smaller eruptions that preceded the largest eruption. So yeah, there should be. I would assume that I would consider there being ample time, but I guess what I would say that it also sort of depends on folks who might be in an affected area to take warnings seriously and start taking action. So yeah, unfortunately, it's something we can't say for certain, but globally, said there's almost always hours to weeks of notice before an eruption happens.
Okay.
And the more monitoring equipment that there is on volcanoes, the better we can sense this stuff. And so yeah, it's something that we're working on increasing our capacity all the time and trying to be better at detecting signals and understanding, being able to really distinguish the signals from the sort of noise, so to speak, like what is background activity. And so that's something we're working on improving every day. So
if you hear at work that something's going on down here, would you give us a call?
Sure. Yeah. It'll go out on all the social media and all of the bands, just as you'll know as soon as I do if you're signed up.
Okay. Another question, might a Cascadia subduction earthquake have any effect on Newberry?
That's a good question. So historically around the world, there's no signs that big subduction zone earthquakes have triggered any sort of eruptions. And I'd say like this is sort of speculation, but the one caveat would be that if a volcanic eruption, if a volcano was in a period of very heightened unrest, it might be the last thing to kind of shake something loose. But in general, and so the last big Cascadia subduction zone earthquake was in the year 1700, and there's no eruptions occurred in conjunction with that. At least at least not like right immediately. I don't think we know the full time scale of some of these things, but also you look around the world and it's not been a pattern that's been detected. The big earthquake that happened in the Tohoku earthquake in Japan, that's a very volcanic area as well. They didn't trigger any eruptions. Down in Chile, there's been, in the last 20 years, there's been at least one really, really large earthquake on a subduction zone earthquake, and that didn't trigger any, didn't lead to any additional elevated volcanic activity. And so, yeah, luckily there doesn't appear to be any linkage between that, aside from the fact that the subduction processes are causing volcanoes to exist, but it doesn't seem like there's any mechanisms related to the triggering by big subduction zone earthquakes, thankfully.
Yeah. That's it for questions.
Okay.
Thank you, everybody, for coming to this class. Thank you, Joy, for the presentation.
Absolutely. Thank you all so much for being here.
Wait a minute. Are there any estimates on how long the Sun River area was underwater until the lava flow from the lava butte was eroded at Benham Falls?
Ooh, that's a good question. There's a USG, if you go to the Newberry USGS webpage, there's a section of publications, and there's a field guide, I believe, in there from a field trip that a lot of this information came from that I shared today. That I believe there's a slide in there or a page or two in there that show what they think was the extent of the flooding, but I don't know if they cover how long that would have taken place.
Okay. Okay, I think that's all.
Okay.
Again, thank you, Joey. This was great. I really appreciate all the time you put into this. And this was good info for those of us that live in the National Volcanic Monument. Thank you.
Yeah, well, much appreciated. Thank you all so much for coming, and thank you for the invitation. I very much do appreciate it.